VSPER diagrams. We're going to be looking at different molecules. And by the end of this video, you should be able to figure out the shape of that particular molecule. VSPER is what we usually call it. The right way is VSEPR because it stands for valence shell electron repulsion pair, but VSPER, it's a lot easier to roll off the tongue, so we just say it that way. I want you to look at methane here. This is what you're normally used to seeing. Methane or carbon tetrahydride. All of these angles here seem to be at a 90 degree. 90, 90, and 90. However, we are using a two-dimensional plane on this blackboard. What it's supposed to be is actually something like this, where you have your hydrogens on the outside. And it looks this way because we're in 3 dimensions. So all of these different orientations, right? So this is one orientation, this is a different type of orientation in space, and this is another different orientation. And all of these have the same angle, but it's not particularly 90 degrees. It's actually 109. 109.5. Same thing here, like 109.5. Okay, and same thing here. Because it's this kind of shape, we assume that another molecule, like ammonia, is going to behave the same way if it looks quite similar. Ammonia also has these 4 different areas. This one, this one, this one, this one, just like CH4. 1, 2, 3, 4. The big difference, though, is obviously this unbonded electron lone pair. And because this repels more than bonding electrons, so these are the bonding electrons, right? Because this one repels more, as you can see, I've oriented it down a little bit this way, and this one a little bit that way, as opposed to like here and like here. This means then rather than a 109.5 degree, it's going to be smaller. So it's going to be actually 107.3 degrees. If I want to show you what the proper terminology is for every single one of these, this one here is the central atom. The central atom is typically placed for the A. So this here would be A. The X's stand for the bonded surrounding atoms. So that would be this, this, and this. Hence why we have it labeled for the X. So right now this is AX. But how many AXs do we have? We have 3 of them. So we're going to put AX3. Oops, sorry, I forgot to put this one here as an X. Okay, but also, honestly, you could just turn this to an H, turn this to an H, and turn this to an H for ammonia. Okay, X is just a representation for that element. So AX3 for now, but we cannot forget this lone pair. So that would be an E. So for this section over here, E stands for the lone electron pairs. This picture here shows you in much better detail how the orientations are being placed. So let's have a look at our CH4. Our CH4 has 4 of these segments. 1, 2, 3, 4. So let's look for that one right over here. 1, 2, 3, 4. You notice how they are oriented. Looks much better this way than on an actual board the way I drew it, so it's better for illustration purposes, for comprehension. And every single one of these bond angles here is 109.5. Similarly, looking at this picture here, our tetrahedral, 109.5, but a trigonal planar, as we can see, there are how many segments? 1, 2, 3. So this one would be an AX3. And the way they're oriented, the bond angle is 120 degrees. Much larger than this 107.3. And it makes sense because it does not have this segment over here. If we get rid of that segment, of course, these are going to go in that direction because, of course, these electrons want to stay away from each other as well. Hence why it opens up the angle and becomes bigger. Hence the value is 120 degrees. Now let's have a look at the different types of shapes. We'll start with a linear. And for the linear shape, this is something you need to memorize. It is going to be an AX2. Now, how does that AX2 look like? An AX2, of course, A is the central atom, it's in the middle, and then we have our X's on the side, and they're going to be connected with a bond. What is the angle between these two bonds? Quite obvious, 180 degrees. Because it's 180, bond angle is going to be 180. So we could say bond angle is 180 degrees. A good example of this would be CO2. So that would be a good example, CO2. Or we can just write it as CO2 here. Let's do trigonal planar. Trigonal planar is an AX3 shape. AX3. For a trigonal planar, we have our A's in the middle, but then our X's are now going to be spread out a little bit more because we have an extra X now. So let's have an X up there, an X on the side here, and an X there. We've already looked at the previous example with 120 degrees, so you should already know that by now. So the bond angle here is 120 degrees. AX3 is known as trigonal planar. But unlike the first example for the linear, there is another subcategory. Trigonal planar, again, is the base name. I'm also going to put here or AX2E. AX2E is a bent shape. Now it's bent in reference to the trigonal planar subcategory. Category. So bent is a subcategory of trigonal planar. It's just a bent shape. Let's have a look as to why. It looks this way as a bent shape. If I were to draw my A over here, I had my X up here, but instead of an X, now I'm going to put these two electrons, the lone pair, as opposed to the X. And then these two X's will stay the same. Because these X's stay the same, I might actually want to bring this a little bit closer downwards because, of course, this one has a lot of repulsion. It's going to be at a smaller angle now. So rather than 120 degrees, it's going to be less than 120. So let's say, for example, something like this angle over here, this would be less than 120 degrees. So this one here, bond angle, was 120 degrees. This bond angle here is going to be less than 120 degrees. A good example for this one would be BH3. Next, let's look at AX4. So by now, you should have already realized the pattern. The pattern goes up by ones, right? So AX4, it has subcategories as well. let's just look at the main one. The main one in here, the AX4, is called tetrahedral. Tetrahedral, we have an A in the middle here, and we should be already familiar with the X's by now. So these are in different orientations. And we've already established that it's 109.5. So let's say on this one, all of them 109.5. And bond angle, we've already written it down as BA. It's equal to 109.5 degrees. And one of our examples here would be CH4. So as we are going through this, we should be memorizing it at the same time. AX4. Subcategory for AX4 is AX3E. AX3E is called trigonal pyramidal. Sounds quite similar to trigonal planar, but it's not trigonal planar, it's trigonal pyramidal. It gets even more complicated when we go even further down, when we see trigonal bipyramidal. But for now, this one is trigonal pyramidal. Trigonal pyramidal. It's going to look just like this, just like the previous example. But what did we do in the previous example? Just got rid of that X. And then we need to make it into a lone pair. So now we have that lone pair over there. And then everything else kind of stays the same. The X is here, this X is here, and that X is there. So the bond angle, instead of 109.5, it's going to be less. So this one would be less than 109.5. If you want to be extremely accurate, I believe it's 107.3. Different textbooks have it differently, but what I'm seeing here is 107.3 degrees. An example, we already looked at it, was ammonia, NH3. So that's one subcategory. There is another subcategory named as AX2E2. So all you're really doing is decreasing the number of the X's, but whatever you decrease, that same factor needs to be added for the E's. So we got rid of another X, so it'll be AX2, but you got to give that to an extra E. So rather than an E, now it's an E2. And D summed up still gives you 4, so that's not an issue. This here would be called bent. Okay? Not this bent. This bent is under this one, the trigonal planar. This bent is under the tetrahedral. Now, let's look at the drawing. So A, again, there was the lone pair over there. Now we're going to have two lone pairs. So if this is one lone pair, let's have another lone pair. Oops, let's have them a little bit farther apart. It makes a lot more sense when they're farther apart from each other, just because they repel so strongly. So if that's like that, that's like that, and then maybe we could have two more X's down here with a normal bonded line, that orientation. And this one is going to be, again, less than 109.5. So maybe this one here, less than 109.5. If you want to be extremely specific, instead of 109.5 lesser, it's 104.5 degrees if your teacher requires you to memorize that. And as we continue to keep going down, we need to hit AX5. And then after that, we need to be hitting AX6. And then we'll be good. And then we'll do some review questions. Next, we have an AX5. So the AX5 kind of looks like a star formation. Let me show you what it looks like. But first, the name for AX5 is trigonal bipyramidal. Now, the trigonal bipyramidal has an A, of course, in the middle. And where are the X's going to be represented? There is an X up here, an X down here, and an X to the side. And we're going to have our other ones in the other orientation in space that way. Now, why is this important to draw this way? Because now we need to start looking at the north-souths and the equatorials. The north-souths, which would be represented by these orientations, for example, would be at 90 degrees. So this one would be 90 degrees. But the equatorials, so these ones on the equatorials, is going to be 120 degrees. So this here would be 120 degrees. The bond angle, what did I just say? The 90 degrees is for north-south. And 120 degrees for the equatorials. A good example for this one would be phosphorus pentachloride. So maybe I'll write this here. Phosphorus pentachloride. So that's AX5. It has more subcategories as well. Let's look at the AX4E. AX4E is known as the seesaw. How would this one look like? The seesaw has exactly the same as this. We always just preface it from what we were working with before. If we had an A here, X is here, but this one here on the side, for example, right, we're going to just take this X and we're just going to put this as a lone pair. So there is our E. So we need 4 X's. So we just need to draw 2 more. So we're going to have an X here where it was, and this X here. That's where that was. Now, what are the bond angles going to be? The bond angles, let's say for this one in these orientations in space, is going to be less than 120 degrees. And then for the north-souths would be somewhere here. So this one here would be, 90 degrees. So our bond angle is going to be less than 90 degrees. Oops, sorry, forgot to put less than. So less than 90 degrees for the north-souths, and less than 120 degrees for the equatorial. Next, below the AX4E is going to be AX3. Add one more to the E, so it's going to be E2. So we have AX3E2. Now, how is AX3E2 going to look like? We'll have it. It's called T shape. And instead of these having a lone pair, both of these now are going to have a lone pair. This orientation and this orientation in space. So let's copy it out as it is. But rather than the bonds with the surrounding atoms, so atom here is going to become the lone pair. This is going to be the lone pair. So now this is an E2, and we need to have 3 X's. So we'll have an X here, an X here, and an X here. So those atoms are going to be bonded there now. And in terms of the bond angle, it's going to be less than 90 degrees for the north-souths only. So just these ones, like north-souths, these are going to be 90 degrees. So bond angle here, less than 90 degrees. So less than 90 degrees for the north-south. There isn't any for the equatorials. Now let's look at one more subcategory. So there is one more. We have AX2, now it's going to be E3. So it's kind of like flipped. This is going to be called, surprisingly, linear. Let's draw it out. How is it going to look like? Well, we have our A. Now, instead of this one having a surrounding bonded atom, it's going to be a lone pair. So this is a lone pair. This is a lone pair. Now this is a lone pair. Our X is here, X is here. So if I got the bond angle for, let's say, something like that, this would be 180 degrees. So the bond angle here would be 180 degrees. Now let's look at AX6. we have octahedral. In octahedral, this is going to be the base, and then there are two more subcategories below it. So for now, the octahedral is going to be AX6. Let's spread them out. So the X's are going to be, here, another X maybe here, another X here, another X here. Just spread out as much as you can. And this is going to be an orientation. This over here, and this one over here is going to be in its own orientation, and this one in its own orientation in space. How is this going to look like? All of them are going to be 90 degrees. So the bond angle is going to be 90 degrees. Very clean cut. If we look at subcategory below that, it would be AX5E. AX5E would be square, pyramidal. And this X over here is going to be a bond angle, a lone pair. So this X kind of stays the same, and then everything else honestly stays the same. And this one up here stays the same. This one here stays the same. It's called square pyramidal. Bond angle would be negative 90 degrees for the north-souths only. So there are no equatorials here. Lastly, we have square planar. We have AX4, give an extra one to the E, so you get AX4, E2. This is called square planar. And the square planar, these X here is going to turn into a lone pair. Everything else stays exactly the same. No change. And this one, all the bond angles, just like the octahedral, is going to be 90 degrees. These are the shapes, AX2 all the way up to AX6 and their respective subcategories. Let's do this question together. Use the VSPER theory to predict the shape and the bond angles for SO4 2-. Well, let's first do the Lewis structurals to make our job easier. So we have 1 sulfur, valence of 6, plus how many oxygens? We have 4 oxygens, each one with a valence of 6, and then we're going to add 2 electrons. In case you don't know what I'm doing here, please look at the previous video on Lewis structurals. So they're all going to be summed up to 32 electrons. So if we just do a 32 minus 32, it's going to give this a 0. So this means there are 0 electrons around the central atom. So if we have our sulfur here, 1, 2, 3, 4, 5, 6, they all need to be bonded because none of them can be lone. If we have just our oxygens spread out on the side, we can bond this one here. We can bond this one here, bond this one here, bond this one here. However, this is not enough. All of these need to be bonded, so let's bond an extra one here to double bond and bond another one here to double bond. Now that all of these are double bonded, we have 1 bond, 2 bond, and 3 bonds. If there are 3 bonds, then you only have to do 1 lone pair. If you have 2 bonds, you have to add 2 lone pairs. If you add just 1 bond, then you have to add 3 lone pairs. So this one here is 2 bonds, so we'll add 2 lone pairs here. This one here is a single bond, so we'll add 3 lone pairs here, add 2 over here, and 3 over here. Now, we have to look at the formal charges just to make sure that we did it right and they all kind of balance out and is quite stable. So our sulfur here has valence of 6 minus how many bonds? There are 6 bonds, 0 dots on the outside, 0. Next we have formal charge for the oxygen. And the oxygen here is going to be double bonded. Okay, so I'm just going to put here as double bonded oxygen. This oxygen over here has valence of 6, subtracted by the amount of the bonds. There are 2, and the amount of dots around it is 4, hence why you get 0. So far it's looking pretty good. Then we have our single bonded ones. Oh, by the way, this double bonded one, this one, which is what we just did, we can do the same thing here as well, but they're pretty much identical, so we can just times 2. Then we do it for the single. So we look at this one over here. We have 6 minus how many bonds? 1 plus how many dots? 6. You end up getting -1. So if we have to multiply by 2, that's fine, because this and this are identical. Does this make sense? It does, because these negative ones means that they are somewhere in this illustration. They're going to be placed right over here. Right over here, because these are the single bonded ones, right? There's a single bonded and this is single bonded. Hence why our SO4 2- at the beginning makes sense, because those 2- means that it gained 2 electrons to get to that state. Now, what is this? Is this a tetrahedral? Is this a trigonal planar? Should be quite obvious. S is going to be represented as A. X is going to show how many elements are going to be the surrounding atoms that are bonded. So we have an oxygen here, an oxygen here, an oxygen here, and an oxygen here. So there's 4 of them. And there's no lone pairs on the outside of that central atom. So there is no E at all. So just going to be AX4E. Therefore, this is going to be tetrahedral. Let's do another one. Let's look at CH2Cl2. There is 1 carbon, and that's going to have 4 of them, 4 valence, plus 2 carbons. And the carbons have, the chlorines. This is the chlorine, so there's 2 chlorines, that's going to have a valence 7, and then there's going to be 2 hydrogens. So you get the sum of all of these, you end up getting 20. Now, just get 20 minus 16, which is the greatest common multiple of 8, without exceeding this 20, it's going to give you 4 electrons. There should be 4 electrons on the outside. So if we draw our carbon, 1, 2, 3, 4, is the central atom, lowest electronegative element. Then we have to get our chlorines and our hydrogens just kind of surrounded on the outside, and let's just bond them together. However, we need 4 electrons on the outside. How does that make sense? Are we stuck? Is this an exception to the rule? Yes, it is an exception to the rule, because carbon can't have an expanded valence. So we did some examples for the Lewis structurals, if you want to see that video, where we got like phosphorus, for example, it had an expanded valence, right? Carbon can't have an expanded valence, though. It can't have more than 8, like all in total. So if this was 1, 2, because they're sharing electrons, so that would be technically 2. This would be 3, this would be 4, this would be 5, this would be 6, this would be 7, this would be 8. It cannot exceed that. It can't have an expanded valence over 8. It can't have that because there aren't any d orbitals in the second energy level. So maybe I'll write that here. So it can't have an expanded valence because there aren't any d orbitals in the second energy level. Okay? Because it's in the second period. Because it's in the second period, it doesn't reach the d orbitals. The d orbitals starts on what? 3d. There is no 2d. So when you start to add all of these electrons in, right, we can have up to 10 for some of them, right? You can have up to 10. But carbon does not fit there, so it would not be able to do this. So that's going to be it. We can't do anything more to it. This is an exception to the rule, so we can just quickly do our formal charges. Our formal charges here for our carbon is going to be 4 minus 4 plus 0, because there's 4 bonds over here, and then there's 0 dots, so there's going to be 0. Then we have our formal charge for our hydrogens, and our hydrogens here looks pretty stable. They usually are 1 minus 1 plus 0, okay, because one bond, and then there's no lone electrons, no lone dots, and then it just becomes 0. There was 2 of them, so we just did that one, so we can do that identical, so we can just times 2, and then we can do our formal charge for our chlorine, and our chlorine here is valence of 7 minus 1, right, because there is only 1 bond over here, plus how many? We should have added the dots here, so again 1 bond means that there are 3 lone pairs, so 6 dots are on the outside. 7 minus 7 gives you 0. And then this happened twice, so if we did that for this one, we could have done it the same for that. So they all kind of check out. It's quite stable, and it makes sense because our CH2, Cl2 does not have any charge here, so we're good. Now we just have to determine what type of shape is it. Well, we look at our central atom, that would be our A, so it's an A. How many X's are there? Where there's 1 element, 2 element, 3 element, 4 elements bonded to it, so that's an AX4. Are there any lone electrons, lone pairs on the outside? There isn't, so there is no X, so that wouldn't exist, so it's just AX4. So this is actually also tetrahedral. All right, let's look at ozone. If we look at ozone, O3, we do our normal counting of electrons, so there's 3 of them. Multiply 6 gives you 18 electrons. This is where it can get a little bit tricky. First, find your greatest common multiple of 8 times 2 obviously gives you 16 to not exceed 18. So 18 minus 16 gives you 2 electrons, so we must have 2 electrons on the outside. Now, what individuals may do is kind of maybe plant them this way, and they want 2 over here, and then they know that oxygen tends to have 2 bonds like that. This may be what they're looking for. However, if you were to add up all the electrons belonging to this central atom at this very moment is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a problem. It cannot have 10. It cannot have an expanded valence like carbon. So how is this going to work? This one definitely would not work out, but there is a way to be creative. I would like you to give it a try on your own. Pause the video, figure out a way where you can have 2 electrons on the outside of that central atom, but without exceeding 8 electrons that belongs to this oxygen at this moment. You cannot exceed the octet rule. Please give it a try right now. Pause the video. Okay, let's see if you figured it out. The way to do it is you have your 2 electrons here, you have your 2 electrons here, and you have an electron here. This is going to be bonded to this oxygen. These are going to be double bonded to this oxygen. So if we were to count it all up now, 1, 2, 3, 4, 5, 6, 7, and 8. So this is what we end up getting. This is very, very good. If we have 2 bonds here, we have 2 lone pairs. And if we have 1 bond here, we're going to have 1, 2, 3, 4, 5, 6. Right? So we're going to have 3 lone pairs for a single bond. This is how we're going to be doing it. So this here is our ozone. And honestly, we could do our formal charges, but I mean, I think for the sake of time, you don't really need it. Just know what kind of shape we have right now, and it's quite obvious which one's going to be the central atom. We worked so hard to figure that out over here. So this is obviously going to be our central atom. So our central atom here is A for our oxygen, And then we have our surrounding bonded elements here. It's O. So we have AX2, and then has one lone pair, so it's going to be E1 or E. So what is this one going to be? The name of this one, this is therefore going to be called bent. Okay, and it's bent under the trigonal banner, the trigonal planar banner. Let's try 3 questions on your own. This is your question, right? The green question of the day for you to do on your own. So consider the following fluorine-containing molecules to have the general formula XF, the subscript N, so this is the number in question. Arrange them in order of increasing FXF bond angles. In case you're confused of what the FXF stands for, that just means our AX bond angles. So right over there we have BF3, this here we have BEF2, this one is CF4, this one is NF3, and this is OF2. Give this a try on your own, and I will give you the answers shortly. This is the answers.